Hey everybody, Dr. A here, and in this video we're going to be exploring another example of how to use deflection formulas, and in particular we're really going to be looking at a rotation angle formula in this example. So let's go ahead and get started. In the given information, we're being asked to compute the rotation angle at the free end of the beam. We're also being told that the modulus of elasticity is 29,000 ksi and the moment of inertia is 300 inches to the fourth power. So here we have this cantilever beam with a free end at the left side and a fixed end on the right, and it's supporting a uniformly distributed load of 0.1 KLF over its full 20-foot length. So if we were to sketch this deflection diagram, we're going to have a concave down deflection, and it goes out to a taper on the right support, okay? And so what we are really interested in is the slope angle at this free end. So if I put a tangent line at this free end and a horizontal reference axis, what I'm looking for is this counterclockwise rotation angle theta, all right? And so if I say solution here, how do I calculate this? Well, if I go to a table with some pre-derived formulas and I look at this case, I'll find the formula WL cubed over 6EI, and it's that simple, that innocent, okay? Now, depending on what kind of table or what textbook you're looking at, there may or may not be a negative in front here, okay? In any case, what you're looking at here is going to be a counterclockwise rotation, okay? You see, physically, this point is rotating in a counterclockwise fashion, all right? So whether or not you have a negative in front there will indicate if that formula was derived as, clockwise or counterclockwise. And if you're looking at a table from a particular textbook, you should have an accompanying figure. But physically, this is rotating in a counterclockwise fashion. So if I go ahead and substitute values in here, I'll be ready to go. Now, you got to be careful with your units, okay? You have 0.1 KLF. In this case, we probably need to convert everything in terms of inches, okay? So 0.1 KLF will be 0.008333 kips per linear inch, and 20 feet will give us 240 inches. Now, why are we doing that? Well, it's because E and I have units of inches already, and so we need to have consistent units inside of these formulas. So we're going to say 0.008333 KLI times 240 inches to the third power, and then we're going to divide that by 6 times 29,000 KSI times 300 inches to the fourth. And if I punch all of this through, let's see what we get. 240 raised to the third power times 0.008333. And then we're going to divide by 6 times 29,000 times 300. And we will end up getting a value equal to 0.00221 radians, okay? And this is going to be a counterclockwise rotation. So this is our final answer. Now, it's a rotation angle, so you might notice that all of these units will end up canceling out. You'll end up with unitless. But when you're getting unitless as it pertains to an angle or a slope angle like what we're doing here, that is the equivalent to radians. So that concludes this example. If you found this helpful, please hit like and subscribe and be on the lookout for other content like this. Thanks for watching.